let's do another example of finding a function composition and just talk about using it. And let's return back to the example we did a few videos ago when I was talking about sum, difference, and so forth functions and the domains and all that stuff when we were first talking about function combinations. And now let's return back to function compositions and work on number 4 from the packet in 2.6. And actually, one thing that in the notes, what I've listed are the 4 operations or the algebraic combinations of functions, you know, the sum, difference, product, and quotient functions, but I did not actually put in here what the definition of the composition would be. And this is something I recommend adding to your notes for those of you that are actually printing this and using it. But basically, you could write down the definition, which might be helpful just for remembering what f of g of x means. Remember, f of g of x just means f parentheses g of x. For me, this is really easy to remember because that's exactly what, you know, how I'd say it, f of g of x. And that's, you know, what the f circle g, it's like a over of, f of g of x. And g of f of x is defined to be g parenthesis f parenthesis x. And again, that's just kind of like g is being plugged into f, or f is being plugged into g in either case. So let's go ahead and do that for these two functions. Here, f of x was 1 over x plus 1, and here g was the square root of x minus 1. So if we're going to look at f of g of x, that would be, again, how I like to write is just use the definition of what it is. F of g of x always means f parentheses g of x. And to do this, what I recommend doing first is plug in g, because I already know what g of x is. G of x is the square root of x minus 1. So what I'm going to be doing is I'm going to be applying f to the square root of x minus 1, because that's exactly what the g function is. And now, all this means is I'm going to take this expression and plug it into f, because I'm taking f of x square root of x minus 1. Because I don't know what this is, I can't just grind it through a number. But basically, I'm going to be plugging in the square root of x minus 1 here. And since f of x is 1 over x plus 1, because usually I would take 1 and divide it by the input plus 1. But here, the input is the entire g function, which is going to go right in the location for x. So if this is a little bit hard for you to kind of understand, what I recommend is just replace x in f with this, because that's exactly what will happen. Because usually if I'm doing f of 3, that's what I do, right? I change x to 3. Here I'm changing x to the whole thing. And then this would give me my composition of f in g. And again, we might wonder, well, can I simplify this? Should I do anything with this? But whatever, I've created a new function, which again is going to be entirely different than net result of applying two functions in order, g first, f second. Now, if I were to do f first and g second, that would be g of f of x, g of f of x. That would be g, instead of taking g and plugging into x, I'm going to do exactly the opposite. I'm going to take f and plug it into g, where f was just 1 over x plus 1. And again, this is sort of how I imagine in my head. F of x is an entire function, that 1 over x plus 1. So that I substituted into the parentheses because I'm trying to figure out what g of f is. And then I need to, now this means I'm taking g of 1 over x plus 1. Or I can kind of imagine it as taking that and jamming it into there. And again, it's going to replace the x, because usually, well, g of x is, I'm going to take the square root of the input minus 1. And I'm going to do the same thing here, the square root of the input minus 1. Just the input here is quite a bit more complicated because it's an entire function, 1 over x plus 1. And again, I'm kind of imagining taking this whole thing, sticking it in for x in g. And if a function has more than one x, you need to insert that into every position of x as you're applying. But anyways, that gets me this. And again, I could try to simplify that, but at the end of the day, whatever, that is my function composition. Sometimes we refer to these as function chains, In calculus, you have what's called the chain rule. It's a notoriously difficult rule for dealing with derivatives, but it's how we actually determine the operation of a derivative upon functions who have been composed together. And it's a very, very helpful rule for dealing with more complex functions. And really, the idea behind a composition is, well, what happens when I don't just have a singular function, but I have multiple different things being applied all together? And it is not commutative. Remember, commutative is just a term for when the order does not matter, but the order which I'm plugging one function into the other does matter. It gets me different results. These are not the same expression, and it's an important tool for differentiating between what will happen in these different cases. And then we could also evaluate, let's just say at 5 as we did before, that's a typo because we evaluated each of the sum, difference, product, and quotient at 5. But let's say we wanted to do the function chain at 5. Again, one of the benefits of doing this is here I have the algebraic expression for the chain. So let's say I wanted to do f of g of 5. That, we would also refer to this as evaluating at 5. That would just be a matter of plugging it in. So I would have 1 over the square root of 5 minus 1 plus 1. But that would just be 1 over 2 plus 1 because that's the square root of 4. We already did this math a few videos ago. And in the previous video, what we had is like 1/2 times 6. 1/6. Sorry, no, it was 1/6 times 2, or 1/6 plus 2, or 1/6 minus 2, something like that. But notice that it's quite a bit different here because when I'm chaining them together, I actually get 1/3. It's not just an arithmetic combination of the two. It's actually they're chained together in this unique way. And if we were to reverse the order that we composed them in, I would have G circle F of 5, which would just mean plugging 5 into here, which would be the square root of 1 over x is 5 plus 1, then minus 1. And so here I would actually have the square root of 1/6 minus 1, and this would actually not even be in the domain because this would actually produce a negative 5/6. And so we would get something that is not real. And whereas 5 was in the domain of each of the functions individually, 5 is not in the composed domain just because of what has happened. And this is something that you need to know about the domain of a function composition. Actually, I say you need to know. You don't really need to know it. It's not important for this class, but just for the record, why not? It can change the domain completely because when you actually jam two different functions together in this way, it can completely alter their domain by the order that they've been stacked in. So what I recommend is if you're trying to find the domain of a composition, analyze the new function and try to figure out the domain completely individually. Whereas this is actually a little bit more complicated, and I'm not going to ever do this to you because I want you to know the basics of domain, not all of the little individual step-by-step for every single possible function. But anyways, notice that it can change the domains and give you something completely new. Anyways, that will wrap up our talk on composition of functions. Composition is important. We're going to talk about inverse functions next. We're going to do it mostly in class this week. But a lot of these ideas will be important for inverses because there's certain properties of inverse functions which apply towards chaining functions together or composing them. So anyways, that's it for this one.